All right, guys, so let's get started. And today we're going to be doing decision trees, right? It's one of the supervised machine learning techniques, and slightly different in that we're going to be doing, many key concepts in the traditional presentation sense, a presentation, and then we'll get back or switch to our Jupyter notebook, where also, we do a lot of the concepts. And one key point is we've been talking about it, supervised versus unsupervised. We have not seen unsupervised, but it's very easy to understand the what supervised and unsupervised means. Supervised is where you have a target variable, right? So number of runs scored, what might be the stock price for Bitcoin tomorrow, all that supervised. Unsupervised is you don't know. You have all that data and you're trying to figure out something. Like for instance, what's the so you have all the astronomy data and then you're trying to predict some patterns. You have all the national database and you want to predict some patterns. So let's get started. So first is, I mean, these are standard notes that I typically keep. We'll be very hands-on. I think we're extremely hands-on compared to like other sort of courses. Try to be independent. Try to debug as much as possible. By now, you would have understand that code programming is a lot of monotony. Data science is, but some of the best things in life are all mundane, right? Try to debug as much as possible. You have seen me debugging the code, so I don't think there's any issues about that. You've seen the patience, perseverance that it takes. Try to at least in the starting stages debug for 10 minutes. That's called the 10-minute rule. Otherwise, and if you're a little bit beginner to medium to expert, try to at least debug for 20-25 minutes. Struggle. I've been on errors for like days, maybe 1 day, 2 days as well. That mostly happens if it's an unfamiliar topic, like maybe let's say AWS or GCP. But if it's a familiar thing, the debugging rate is faster, right? And how do you become a better programmer? Pair programming is one of the best ways. Like team up with somebody, do some competitions, set yourself for success for long hours. See, long hours is an art, right? What does long hours mean? People say hard work and all, but I just say long hours. See, for instance, I'm taking these lectures, right? What I do is I force myself to do 2-hour sessions, plus some more office hours for something else, let's say cryptocurrency or something, another 2 hours, so 4 hours, for each 4-hour session I at least spend another 4 hours, so those are 8 hours. That's long hours, right? And I know that once sessions are done, I'm really happy. Similarly for you, if you're actually in programming, think of ways to hack your own brain, right? Maybe be with somebody who's more motivated, right? Environment is greater than will until will starts superseding, right? So suppose you're going to go to a gym, try to go, and if you're not regular, let's say, then try and go with the next person who's a little more motivated. Don't go with Usain Bolt, because then you get demotivated, but somebody who's slightly better than you, right? At least 2 or 3 orders of magnitude better than you. And then you start learning from osmosis. So long hours, that's one way. The other way I have learned is competitions. So you can have a group for let's say, hey, you know what, let's make a group and compete. Again, get motivated people. The other one is you could do it independently. I've only seen that works when you're like at least from beginner to medium stage. Avoid copy pasting. It's a hallmark of mediocrity. Stay away from attributes that make you mediocre, right? Because frankly, like, way too many people are there, right? As you know, 7 billion is the population of the earth, right? 90% of them are just right there, and it's very competitive there. And it's actually easy to get. It's a little bit of hard work to get into to excellence, but once you're there, it's great. It's like an orbit, right? So I've written a nice debugging checklist, which I've seen like I make, which hopefully even you should be making. So feel free to add this to your own. Most of them are spelling mistakes. Case sensitive parentheses that's like the most usual problem. Correct path to the data set, that's a session, that's in the beginning. Libraries are not called properly, variables, indentation. For though this is for people who don't know programming. So I was familiar a little with programming. I should do SAS programming. So program, if you know basic programming, like if maybe you're a computer scientist or whatever, or you're a MATLAB engineer, then this wouldn't be that much of a problem. For newbies, this is definitely a problem, right? So again, this is like workout, right? If your abs are weak, nobody's born with best abs. But if your abs are weak, it's okay. Just keep working on them. Many people have weak biceps, right? Perhaps even more so. But again, if you just by practice, you can just become good. Syntax, humongous problem, even for I would say advanced people such as me. Not that I'm telling I'm advanced by many means, but even I make a lot of syntactical mistakes. That's simply because there's way too much syntax, right, to remember. So, but then you should quickly know how to get to Stack Overflow, the best place. Quickly know how to intelligently Google. For those of you who don't know how to Google, this is the recommended book. See, many people don't understand basics, right? Oh, not this one. Where's that book? I got? Yeah, this one. Sorry. Yeah. Okay, there's enough information. There's a really good book. I think it's by O'Reilly. Oh yeah, now it should come. So it's not the software engineering. So basically, how to Google effectively. That's the book. Not search engine optimization, etc. There is one book. Feel free to ping me later, but I hope you get the general idea. There's a very good book that I read a while ago, how to Google effectively. Considering that the hand touches you, at least apparently the average number of Googles, the number of times you search is roughly about 15 times a day, right? And some people a lot more, some a lot less. If you're a programmer, a lot more. So it makes sense on how you want to Google effectively, right? Because if you're doing something 15 times a day, you better do it smartly. So coming back to this, and shape mismatch, that's very easy. Type mismatch, Stack Overflow, how to be smart about that. Okay. So let's get started with our decision tree. Okay, let's go through this small exercise. Okay, so let's say I'm thinking of a random animal, right? And this is going to be a little more interactive. Can you guess the animal based on my answers, right? I'm sure you played this game. I forget what's the name of this game, but you have like 10 questions and then you have to like figure out what I'm thinking of a person, like maybe a famous personality. I'm thinking of Gandhi, but I'm not going to tell that to you. And then the way I tell is, okay, he's freedom fighter, gave us independence, so on and so forth. The first question you ask is he a male? Then is he is he maybe a lawyer or a freedom, stuff like that. So now let's actually literally do this. So if I were thinking of an animal, the first question probably you might ask is, let's say, you know what, does it have four legs? Is it a reptile, or is it like an animal that's extinct or not, so on and so forth. So basically you have a list of questions, right? And from that you start making a mental map of, okay, or like a small uh, mental map of what was said as yes or no and so on and so forth, right? So let's go and look at that, right? So how many legs? So if I say 0 legs, then you probably might be thinking it's a snake. If I say 4 legs, which seems very common, then it could, and then you might want to ask, is it wild? So, and if I say no, then you might say it's a dog, right? So you get the general idea of how I'm trying to, uh, come up, guess the animal. So this was, I went to snake. This is how I went to dog, right? Now, if I say, if it's wild and it has 4 legs, maybe it's a tiger, right? Now, and then you say, okay, number of legs is 2. Okay, that's interesting. And then you say, does it fly? So maybe it's a crow, right? So these are sort of the usual paths that are traveled, right? So basically, you get the general idea that asking the right questions, and you might yield smart answers, and then you continue to ask the right questions, right? I hope this part is fairly intuitive and clear, right? So let me get rid of this drawings, my wonderful drawings. Thank God I didn't draw an animal. Now coming to this, right? The same tree can be mapped to something like this, right? So we have lots of possible animals. Each has a set of attributes. Let's look at one attribute at a time, right? So let's say we're looking at, let me look at cow, for instance. So let's look at this row. Which row? Guys, I'm going to look at only the cow, right? So it's got 4 legs. It's got wild. Sorry, it's not wild. Does it fly? Definitely no. Is it nocturnal? No. Fur feather? No. Is it in a farm? Yes, right? So the same 1, 3, 4, 6, 7, 9, 10, 11. So the same tree was expressed in this 11 by 6, right? So there's 66 data points here, correct? Now, but if you notice, we sort of pictorially represented this far more elegantly. Does it look like this tree has 66 data points? It's a 6 by 11? Definitely not, right? So trees are actually, or you might want to be thinking of trees as something that has rich properties and a lot of information, right? In fact, sometimes, just sometimes, to get a snake, I just went to depth 1. While for the dog, I went 2 depths, right? Twice as deep in this case. So you also are getting a little bit of sense of the intuition of, okay, there seems to be depth, there seems to be the root. Now the root was number of legs here, okay? So if you've understood just the first couple of slides of, how I got a tree, right? And how I got the table, just type tree, TR, tree. Guys, I want you to be very proactive in this session. Okay, excellent. So you've understood tree. Now, you might ask me, hey, what are we actually doing with this tree, right? What's our end objective? Because always, 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 always remember the goal is very important. Nothing matters like the goal. So the goal is always this guy. To arrive at a single class label, right? Now, what is a single class label? A zebra, a horse, a cow, a cat, a penguin, an owl, a fish, a snake, a millipede, a firefly, a butterfly. So here, the number of class labels were whatever one, like I said, 11, right? Yeah. So there were 11 class labels in this case. That's kind of animal. But, got it? So what we're trying to now do is the end goal is to determine the class accurately and learn the tree, right? So what does that mean? Or let me repeat that again. The goal is this 6 by 11 tabular format. Can we learn, can we map it to this kind of tree? That's the goal, right? We want to come up with a very nice, elegant schema like this that will depict a tree, and we'll towards the end, we get all these kind of class labels. Perfect. Let's see how do we do that. So, so at each step, ask the question that minimizes uncertainty. So forget about that right now. Once the set contains only a single class, label it. The sequence of questions or decisions can be represented as a tree, right? So now, some key terms. We already looked at the root. This is the root, okay? The Q1, the first one, number of legs. A node is whatever is happening inside, right? Q2, Q3 are all nodes. So Q1 is the root. Let me write that down. So Q1 is the root. Okay. This is a node. Of course, Q3 is also a node. I'm not going to write that. These are all leaves, right? The class 1, class 2, class 3, class 4 are all the leaves, right? Depth. Q1 to Q2 is called depth equals 1. Q1 to class 1 will be depth equals 2, right? And height is also corollary coming from that, right? So what is the height of the entire tree? Q1 to class 1 is the entire height, right? So maybe in this case, class 1, class 2, class 3, class 4 all seem to be in like one nice pyramid, but sometimes class 4 can go beneath a little more. Like you have to arrive at class 4 a little more. And then the path is, well, this is the path. Remember how I drew those curly lines? So the path to get to class 3 would be like this. That's a path. And parent and child is also fairly easy. So the parent for Q3 is my Q1, right? And what is the child for Q1? It's both Q2 and Q3. I hope the definitions make sense because they're also, easy to sort of understand. Now, what am I doing? I am doing two things. First off, it goes without any confusion that I am always trying to find the bottom leaves in a way that it comes to class 1, class 2, class 3, class 4. It should not be a mixture of class 1, class 2, right? Now, and furthermore, during the process, I'm actually learning this entire picture. So let's look at how we do that. So what is the best way to split mathematically? That is a question you should be asking, right? Meaning, how do I know number of legs was the best way to pick the top of the tree? First off, can I make a tree with flies? My first question would be, will the animal fly? So first off, I'm asking a question. Can I make the top of the tree flies? Or can I make the question, the top of the tree, the top of the tree as, does the animal fly? Okay. Samiksha is saying no. Vamsi is confused. Shambhavi is saying yes. Pujari? Okay, Vamsi is resounding yes. Lock kiya jaye. Yes. Yeah, you definitely can ask the first question as, can it fly? Somebody might also want to ask, can it be wild? Is it wild or whatever? Is it nocturnal? Nocturnal means is it night or day, right? Is it alive during the night or day or active during the night? So if I have, so how many ways can I pick the tree top? So in how many ways can I pick the tree trunk? 6 ways. Excellent. I can pick 6 ways the top of the tree. So I can make 6 Christmas trees, right? Now, that's the tree top. How many ways can I pick further the second question? So let's say I ask the first question as, is it wild? So then the branches become yes, no, yes, no, yes, no, whatever, right? Yes and no, 2 branches. Then second, in the second format or whatever, second depth, second floor of the tree from the top, how many ways can I, yeah, very good. We can pick 5 ways. In the third floor of the tree from the top, how many ways can I pick? Very good. So total, how many trees at max can I construct? Wait, what? How did you get 21? So first tree, first, the top I can pick 6 ways. Yeah, how much is 6 plus 5 plus 4 plus 3 plus 2 plus 1, Shambhavi? Okay, let's go back to our favorite workbook. So the first tree trunk, or I call it the root. The root can be picked in 6 ways. The first level, everything is from the top. Huh? First level, I can pick how many ways? 5 ways. I know you can't do the mental math, but you can add 6 plus 5 plus 4 plus 3 plus 2 plus 1. No, just do that, guys. Second level, I can pick 4. Guys, all of you have to have a calculator and come to class, right? Keep a calculator, that engineering calculator next to you, or do not open your cell phone. Do not, NOT, open your cell phone and fool yourself that you're actually doing a calculator. I want a calculator. Are we clear about that? If you're clear about that, type CALC. See, it is 21. That is correct. Why did you have to say I can't do mental math and all? It is 21 means 6 plus 4 plus 3 plus 2 plus 1 is 21. Why? So that is the problem. No, commitment is important. Even if you're doing it wrong, it's so the commitment is important. Don't be a cat on the wall, guys. That's the worst thing to be. You do something, it's okay. Do it boldly. Okay, but I don't want to like further be mean. But really, your answer is wrong. As in, not the summation, but the answer is wrong. That's not the answer I'm looking for. Commitment is important, guys. Do whatever you want with strong conviction. Okay. The idea is not to be right or wrong in life. The idea is momentum. The goal is to be wrong, less wrong, less wrong, less wrong. You should have conviction in whatever you do. Okay, coming back. Hey guys, sorry for that. So I was just, we were, before we sort of got interrupted, we were looking at the root can be picked in 6 ways and the next level can be picked 5 ways. So straight away, how many trees can I make? Christmas trees can I make? Just, using first principles or basics. Correct. Perfect. 6 factorial ways. That's a huge number. Remember that, right? Now, there are 6 factorial ways. So that's 30, 80, 240, 480. So 6 factorial is 480, right? Yeah. So everybody understood there are 480 trees I can make just by this animal question from that. Everybody understood that. Type 480. Shit, what am I saying? It's not 480. 720. Yes. Even I can make mistakes, okay? If I ask you to do something, just don't do it blindly. You have to check, double check, triple check, right? Okay, good. Perfect. So there are 720 trees that I can just create with this, right? My assertion, my question to you is, that's just way too many combinations, right? How do I go about picking the tree top? There should be a way to pick the tree top, right? Is that a good next question? If there are 720 Christmas trees, I definitely don't have the time and the patience to figure out the best tree, to study the best tree. How do I go about picking the best tree top? Any guesses about that? Come on, anybody can guess. Both the front benches and the back benches, east or west. Um, Good guess. I kind of will give you like half points for that. Picking the most common feature. Okay, can you elaborate on that, Godhan? Good guesses. Column with minimum categorical variables. Okay, yeah. Make sure I I have an eye out for the categorical variables. Others, come on, Delhi, participate. Gurgaon, Delhi, NCR region. Need the north. Need the capital area. Samiksha, high non-linearity in route. Delhi, you have proved Again, once again, you're from Delhi. I'm just kidding. Okay. Okay, let's look at this. It's actually the hallmark of the question. You understand this concept, you've pretty much understood decision trees. Just this one teeny weeny guy. Let's look at this. So because if I know how to pick the tree top, I know how to pick the rest of it, right? Pretty much it. So it's a concept called entropy, right? Very easy. You probably you've heard it, you've done it in your high schools and all. Let's look at it again. Okay, so let's go back to some small example. Suppose these are the two options. I want to detect if somebody has whatever cancer or healthy. If it's healthy or not healthy. Okay, basically, let me write this as not healthy because cancer might be certainly not a great example. Okay, and I have 5 records here, meaning 5 males in healthy and 5 females in uh, not healthy. And I have 6 folks, so don't know about the gender, 6 folks who are who smoke, and 4 in the rest. For 6 in the healthy column and 4 in the not healthy column, right? Now, which tree do I pick ideally, right? Which is the tree top? Which should be the tree top that I split? Should I? So I can make 2 trees, right? At this time, I can make 2 trees at this time. Let me make both the trees. So let me go back to my workbook. So I can either make smokes, right? Wait, I think it's better to do it on the whiteboard. So I'm here, and let me go here. So my 2 trees look like this. So I first chop it at pick smokes, and since there are seems like 6 and 5, whatever. So there's 6 folk here. 5 folks here. Sorry, 4 folks here, right? And then basically again I ask them the question, male or female, right? And then based on that, again I split, right? Here, and same thing here. As gender here. So here I get again gender. Right? Is this the first tree? Is that okay? Second tree of my 2 Christmas trees were going to be gender. And then I have 5 folks here. And then I have 5 folks here. And then here comes smokes. Is that correct? Yeah. I'm just writing smoke for the in the interest of. Okay. Okay. Everybody clear about how I got this? Smokes and smokes. Actually, you know what? Let me just write smokes. Sorry, just now it looks good. So then and I can further split it. I will further split it here, like this, like this. Yeah, like this, like this. Everybody understood these 2 trees? If you have understood these 2 trees, type 2. Okay, good, good out there. Everybody understood this. Very good. Now I'm saying one of these 2 trees is better, right? And I want you to answer that. Which of these 2 trees is better? Is the smokes tree better or the gender tree better? Okay. Why is smoke better? Can you elaborate on that? Go for it, Samiksha. Non-linearity. Okay. Like you said, I mean, repeating something I might not understand it. Okay, I didn't understand what that is, but that's fine. So let's try to understand this. So, okay, before we high non-linearity. Okay, fine. I'll kind of give it to you. So let's look at this. So let's look at this example, the next example. So guys, take a snapshot of this, right? Now take a snapshot of this guy. Now which tree is better? Sorry, now what will you split it on? Will you split it on gender or smokes this time? Okay, why? Don't tell me high non-linearity in root again. Or you could say, you know, you could continue to say. Anybody else? All right. So yeah, so there you go. So you're getting it. So see, did others understand what she's trying to say? She's saying sharper division. So I want to pick, there are two trees here, obviously. There's just 10 people. I always and always and always and always want to pick the root or the first picking. My pickings should always be in a way where there is what Samiksha calls sharper division or trees where I can discriminate faster, right? So 5 and 4 is very homogeneous. 6 and 4 is very, very highly discriminatory. I want that. I will greedily pick trees or the roots of the trees or the leaves at every point in a way where I can quickly discriminate, quickly differentiate. Why? Because that way I can keep the tree depth smaller. Did you guys understand that intuitively? Why here 6, 4 was the one picked? If you've understood that, type ENT, entropy. We'll see the mathematical formula. Don't worry about all that. That's very easy. Just the concept. 5 and 5 means I'm like a cat on the fence. I don't want that. In decision trees, I want people who commit, who take action, right? So that should be like a 6-4 or a 9-1, or so on and so forth, right? Isn't there a higher probability that stuff would be in the other section? There could be, it's okay. I'm saying of the Christmas trees that are created, the best Christmas tree for me will always see, I'm trying to learn a tree. When I learn a tree, I always want to learn something that's very small, right? So do you want to learn, let's say you're trying to learn a chapter, right, of a book, like just completely cram. Do you just want to learn the short summary or the entire, or do you want to learn the lyrics of a song? The entire song is going to be difficult. I always want to learn the shorter version, right, if there one exists one. So I'll always try to pick trees that are smaller. The depth can be minimized if I start discriminating from the beginning, right? Amsi, are you there? I haven't seen an ENT from you. Ashok as well. So it's a better best case and a worst case complexity. Don't worry about complexity, Jester. That's a good topic. Some of you might be familiar with computer science trees as well. For those of you who are in computer science, trees are similar to computer science concepts as well as here, but they are not the same. Okay, they're not there. There's a little bit of difference. There, I'm always trying to shorten the path. Right, the shortest path is important, which need not mean the tree depth. Okay, and that also depends. So don't bring those elements here just yet. We are going to bring that, but not in this session, in a couple of more sessions later. Probably more than a couple, right? For now here, for decision trees, I only want one thing. Boss, I want to ask you the question in a way that first quickly I eliminate as many possibilities as possible. Right? Let's say Gandhi was the guy I'm thinking in my head. So maybe the best question, just making it up, is dead or alive, as opposed to another question saying, is he a guy or a girl you're thinking about? Now that could be 50-50, right? So I'm just trying to bring that kind of a reasoning up. Okay. Second, the same data set could be arranged in a way where there were 9 LD men, one of the genders, and only one in the other. Here in this case, this gender column is a purer node. So compared to smokes, smokes is still 60-40. Here it is 90-10. So I will greedily pick up gender. You get that? Right? So now I need to introduce a rigorous mathematical formula, which is super easy, on what constitutes purity of the node. That's called the entropy. Okay. There are 2 formulas for that. You learn it in just 5 minutes. Okay, guys. So let's look at that. Okay, this is something we came across. This was a slide what just mentioning. Correlation is not does not imply causation. Let's look at this, the measure of uncertainty. So the formula for measuring entropy is minus pi log pi base 2. Okay, pi is nothing but just that fraction. Like in that case, for gender, it will be 9 log 9, right? Base 2. That's it. Okay. So you're going to be doing this. And the there are 2 ways to measure this. One is sigma log pi log pi, and the other one is 1 minus pi squared. We'll look at both these examples. I'll do one for you, and then you can do the others. Information gain is further divided as IDP minus this fraction minus this. We're going to look at this as well. Okay. Just take a snapshot of this. You don't have to write it down, because the next slide you'll have to be writing down some stuff. All right. Okay, guys, you took a snapshot. Okay. So there are a couple of measures of purity of a node. The first formula I've given you is minus pi log pi. Second one is 1 minus sigma pi squared. I've frequently seen the first one gives great results. Again, how did these formula come? Some mad scientists, mathematicians have just made it. These are hyperparameters as well, right? So in decision trees, one of the hyperparameters is it's called Gini index, I think. Okay, perfect. Now we're going to be doing some hands-on on this, so don't worry about this. So first thing, let me calculate the information gain using entropy here, right? So what do I do? Pi at the top node is 40 divided by 80. So let me do that here. So for the first node, let me calculate that. So 40 comma 40, right? That's the root. So let me calculate the information gain there. So what is the formula? I'm going to write the formula. Minus 40 divided by 80. Log pi. So log of this guy. So log of this guy is 0.5 base 2. So I'm just writing it right now. Okay. Minus the next one element is also 40, right? So 40 divided by 80. Again, log base 2. Log 0.5 base 2. Okay. Next, first depth, first level. So now there are 2 guys here. So let me look at both these guys. 30-10 and 10-30. So 30-10. So first level has 2 elements. So I'm going to write both of them separately. So minus, guys, help me out here. 30 divided by, again, 40 elements. Log 3 divided by 4 base 2. Let me just double check if this is going correct. Yeah, 3 by 4 log 3 by 4 plus 1 by 4 star log 1 by 4 base 2, right? This gives me for that small leaf. Now this other leaf is there. No, there's another leaf with 10-30 elements. So if you actually rearrange this, you'll pretty much know that the numbers are the same, right? It will be the flipped versions of these, in fact. So I'll just do that here. Okay, so that completes first level. Now let's look at second level. Is there a second level? Okay, there's no second level. So I got values of 1. So if you calculate this root, you get 1. It so happens it's 1. Okay, need not be 1 all the time. So first level, if you calculate, I think it's 0.81. 0.81 and 0.81. So there's no second level, sorry, right? So now the IG is defined as 0.81 plus point. So when I go traverse across that, I need to sum all the entropies below minus 1, right? So how much is that? Should be 0.81 times 2 minus 1. 0.62 is the information gain. Okay. So when I construct the tree like this, 0.62 was the information gain. So if I construct the tree, let's say 40-40, forget 40-40, let me just do 20-60. Can you now do the information gain? And so second level will be 30-10 and 10-30. Can you now tell me the information gain quickly for this? So this you just do it right now in classwork. Guys, take 2 minutes. Your time starts now and tell me the classwork right now. So this is the root. This is the root and this is the first level. So first level answer is easy because I've just done it. Tell me now this. If you're clear about this, type CV and tell me the answer. Okay, I'm sorry, just a slight caveat change in the formula. It's 1 minus half the percentage of that. Okay, one second. So it is 1 minus, I beg your pardon, that's the wrong formula. My mistake. So half the records are here into half the records are here. Okay, so this should give you 1 minus 0.8. So that's 0.19. So the information gain is 0.19. Okay, now find the IG here. If I split it here. Guys, are you clear about this? If you're clear, type CV. CV means classwork. If I'm just going to do it in 2 to 5 minutes. It's so 60 by 20, you know. So it's minus 20 by 60 log 0.3. 2 by 6 I've just kept as 0.3. It's 0.33, right? Then 3 log 3 base 2. Oh shit, sorry, my bad. 20 by 80. 20 divided by 80, that's 0.25. 25. So 20 divided by, correct, it's 0.25, and then 80 divided by 20, that's 4 log. And now it should be right. Okay, let's put this now. So this is wrong. So let's look at log 0.25. That's minus 2. Log this piece is minus 2, so this is 0.5. So first value is 0.5. So you get 0.5 minus 4 log 4 base 2. That's 2. So this guy is 2. 4 2s are 8. I'm getting minus 7.5, right? Oh shit. Okay, damn. I don't know why I'm making so many mistakes today. Yeah. So 80 by 60 is 80 is 0.75. She's right. 0.75. So I have to check 0.75. So the first term is 0.5. Is that correct? First term is 0.5. Second term is log 0.75. I'm getting some 0.75 times 0.415. Let's check that guy. 0.75 times 0.415. So that's 0.311, some nonsense. So you get 0.81. So I'm getting 0.81 plus 0.31. Yeah, so that's 0.81, right? Sorry, I don't know why, making a lot of arithmetic mistakes today. 0.81. So you get 0.81 minus 0.81, right? So IG is going to be 0, very close to 0. Okay, guys, you understood this? Did everybody get 0, or in principle, do they know now how to get 0? If yes, type IG. You got two values. One is 0.19 and you got another value as 0. You got IG. Very good. Now, which of these trees will I select? I will select the tree calculation that has least IG. Okay. So I will select this tree. So for all the Christmas trees, first what do? All the 6 factorial trees, I'll calculate the IG. So I get 6 factorial IGs. And then I'll pick the one which has the least. Okay. So that is the greedy method that the scikit-learn algorithm is doing on the back end. I just wanted to show this to you so that you understand and you'll never forget what happened, right? Now you took about maybe 5 minutes with all these painful logarithms. Hence decision tree, is it a slow algorithm or a fast algorithm? It is a relatively slower algorithm, because unlike the linear regression, there is this icky guy here. There is a log calculation. There is a logarithmic calculation. Whenever there's a logarithmic calculation and all that, it's painful. Okay. Because you have to find these values, then you have to build the optimization function. Means the sum of the residual square should be very, very less, something like that. There's a similar algorithm going on. But here, even before that, there is this greedy step, right? Decision trees typically are slow. But of course, if you, and they're memory consuming, because why? Because even each of these exponential logarithmic terms, etc., are both difficult to compute, not difficult, expensive to compute, and they occupy a lot of memory space. Okay, so you have the intuition. So I'm going to pick tree B. Okay, so now let's go back to the classwork. Same thing, change it to Gini, the Gini method. It's 1 minus pi square. You get similar answers. Okay, I'm not going to do this. I'll let you guys do it. This is the same concept, but in a slightly different formula. Okay, so perfect. So let's now start looking at some of the more useful properties. Just few quick notes. So this is how your classification. So classification for decision tree is very easy, right? So it's going to calculate the probability of all the classes reflected and start doing all these calculations. Okay, so you can fairly understand quickly, just like the animal example. Now for regression, the slight caveat is, does decision tree do on regression as well? Yes, it does. Actually, it does work well on regressions, right? The small trick that we use to work on regression problems is the average or the median value of the target attribute is assigned to the query type, right? So if it's runs, right? If you want to predict the runs or whatever, the algorithm inherently takes the average and then makes like a small decision tree splits, right? So tree creation splits into subsets, and further subsets are sort of built, and then the algorithm keeps going. So this is not very difficult to sort of also visualize or think about, and we'll see this. We are going to see this a lot more closely. Now, what might be important to us is the loss function. Turns out the loss function is not our sum of the square errors. Have you seen the sum of the square errors? Yes, we have seen the sum of the square errors in the linear regression, right? So this is one of the first algorithms that um, has slightly different and also very slightly similar loss functions. See, the loss function represents the loss of impurity in the target column, right? The requirement here is to minimize the impurity as much as possible at the leaf nodes. So, like I said, the greedy picking up of the algorithm itself is the sum of is the loss function. Now you've done this just now, right? Calculate the IG across, check that. That's precisely what the algorithm is also going to do. It's going to minimize across all of these, but you've just done it for one node, right? Like one depth. So you can do it for 2 depths, you can do it for 3 depths, so on and so forth. However, there's a slight concept. So instead of linearly working on 720 trees, um, you can kind of make it a little faster by using small tricks. And the way you would do that is picking up. Now, there's this concept called greedy. We're not going to go too deep into it because, again, it comes from computer science. But what I'm trying to tell you to think is definitely the search space is not 720 trees. The search space becomes far lesser. So you might not even do all 720, you'll do less than half of that. So straight away, a little intuitively, you can figure out that I need to search only 360 trees, right? So there are some few concepts there where you can decrease the search space. Now, purity of a node is the measure of the homogeneity in the target column. That it comes evidently from what we have worked on, right? Now, this is a tree, how it looks like. We are going to look at this a lot more closely when in our Jupyter Collab notebook. Okay. First question, just randomly asked questions. DTs only work for classification algorithm. Is that true or false? False. They work well for both. Okay. Answer is indeed false. So now let's look at a few of the evolution of our Python scikit-learns. This is the same for R. You also know about R in terms of, at least you probably have heard about it. It's another scripting language, very similar. So the first version of decision trees when they came were the ID3, right? Very old, again, vintage. You don't have to learn too many things, but it introduced this concept called greedy. Okay, greedy is actually a technical word. For those of you who are kind of interested, feel free to read it up on it. Not many questions are asked on greedy algorithms for data scientist students. However, depending on where you're interviewing, like for instance, Google, etc., ask questions on these because they want all-rounders. They want people who do well on data science plus who are familiar with CS. They're going to be looking at CS as well. This is one of the only few courses that's actually doing that. However, but if you're applying to like companies like, let's say, Deloitte or whatever, the second or third category of companies, they won't look at this too much, right? Because now people not just want the best machine learning algorithm, they want fast machine learning algorithm, right? So trees go to a maximum size before pruning. We haven't looked at what pruning is, but we'll see that, right? Now, one way to sort of think about pruning is prunes when the tree grows, you want to cut it. Now, what is cutting? You are going to really literally chop off some of the bottom parts and pretend that the algorithm never learned it. Why? Because you want the algorithm to start generalizing better than being specific, right? So what happens if the tree is 3, depth 4, it's great. But if the tree is depth 10, depth 11, what starts happening is it's starting to uh, memorize each point, right? So again, Samiksha, so optimal search trees, etc. Those are slightly computer science concepts. There are interesting parallels here, but they are not the same here, right? We are getting an optimal tree, but it's not a search tree. So there are other kinds of trees, guys. So in computer science, you have trees that optimize for search, right? You want for retrieval. We are not optimizing for retrieval. We are optimizing for information gain, right? You've seen that. You've just done that. So there are those distinctions here. Now, coming back to this, is there a way not to compute 6 factorial? That's correct. Each additional classification goes at, so that's where the greedy piece comes in, right? So we haven't, like I said, we haven't got to all of the depth of the greedy piece, because honestly, that's be encroaching on the territory of CS. What I want you to have is the outcome, meaning the such space is indeed not 6 factorial. It's far, far lesser because of this concept called greedy, right? The such space is not 6 factorial. In fact, it's much, much lesser. Okay, is that fair? Now, let's look at a couple of other key concepts from at least a machine learning perspective. So C 4.5, when it came, it ruled, pretty much the world there by overcoming limitations of. So let's just look once at what greedy algorithms are, so that you guys know what we are not covering. So greedy algorithm, it solves the problem heuristically by making the locally optimal choice at each stage. So those of you who are computer scientists or who have a little bit of familiarity, I mean, those who are pure machine learning guys, don't worry about this. So the knapsack problem, Dijkstra's, there are lots of other kind of ways to actually, in a tree, given a tree, you can pick the next node, not using just a factorial way, but a little lesser than that. Okay, that is what I want you to leave it. If you can appreciate this, that there's a method to do that, that's enough. You don't have to know why and how it does that. If you want to, just go ahead and look at these additional nodes. So that's all there. No, gradient descent is not based on this. Gradient descent is not based on a tree. It's not based on it's based a little bit on a greedy choice. There are elements of greedy choices here. We are going to look at gradient descent a little later, not now. Okay. Guys, don't try to mash up concepts. Try to independently assess and appreciate each concept. And if they make a homogeneous way for your understanding, that's fair. Don't try to quickly associate too many things. Okay. Yeah, gradient descent has elements of the greedy. But it's good. It's good. I'm not trying to, like impede your growth in any way. In that, I do want you guys to think, etc. But try to come from a blank canvas, right? So greedy algorithm, by now you would have known, it is actually a very big problem. It happens all the time. It's an old problem in computer science. So here is a graph. It need not be even a tree. It's a graph. Then how do I go to the next phase? So let's say I'm in Bombay and I want to go to Delhi. So greedy algorithm can work there as well. Need not be a tree. Okay. So coming back to where are we? Okay. So C 5.0 was the last I checked, the best version of, or the latest version of the decision tree algorithm. Works best. And somehow he's optimized it a lot more. This is like AMG. Okay. You know what AMG is, right? So the story is Mercedes. So there's a province in Germany called Bavaria where all 3 cars are made. They only do 2 things: beer and cars. So that's Bavarian Motor Works, which is BMW, Audi, and Mercedes-Benz. All the guys just talk about these 2, all the men and women, I mean. And AMG was this showroom, not showroom, like a mechanic who would just take the cars and make them much faster. In fact, so after like decades, the AMG became so popular that Mercedes just went and acquired it. So similarly, all these C 4.5, then that becoming C 5.0 are all add-ons, and they become really big. Okay. So think of these like that. So just generation improvements like iPhone 7, 8, 9, 20. So the decision tree algorithm is fairly straightforward. It looks not, I mean, unsurprisingly, decision tree regressor, and the decision tree classification is called decision tree classifier. Okay. So we're going to look at a few of the hyperparameters and then go back to the notebook and check that. Decision trees. Let's look at some of the advantages. Simple, fast in processing, can deal with missing data. Yeah, it deals with missing value, handles numeric and categorical variables. That's the C 5.0, okay, not the old ones. Disadvantages, often biased towards bits or features that have high number of levels, which is cardinality. So if you have too many cardinality, it might actually be biased towards it. That's a problem. You can actually also nicely mathematically prove it. We are not going to do the proof. Small changes in training data can result in huge changes to the logic, right? Remember how in the gender and the smoking, I just changed 9 and 1 and the entire problem flipped, right? So that can happen. That's actually not good, right? Um, Large trees can be difficult to interpret. In fact, linear regressions were fairly robust, right? Even if you change the data a little, it's not going to move so much because it's so heavy. Trees are not like that. Trees are brittle, but they are very precise and good. You know what I mean? So let's look at this now. Okay, so there are bunch. So trees, decision trees are very prone to overfitting, far more so than linear regressions, right? You can get a sense of it by now because they try to learn every data point. So what is the tree actually doing? You're sending all these velocity raptors and you're trying to learn the entire space, right? So every data point is trying to be learned, right? So that's not good because I want to generalize well. Now, so decision trees do not assume a particular form or relationship between dependent and independent. Uh, it's not a parameterized algorithm. You can use it for anything. Decision tree is my base model. In fact, XG boost, extreme gradient boost, which has won so many Kaggle competitions, is the best decision trees. Like decision trees are the basic building blocks. I don't even use linear regression anymore. I mean, that's just an open secret. So second point, don't worry too much about that. If let's unconstrained decision trees lead to overfitting, that's like the common problem. So we have already seen this. So we do have ways to regularize. We have seen the ridge. You've also not worked on lasso yet. You appreciate it and you know elastic net, right? So regularization parameters depends on the algorithms used. We've seen that as well, right? Bunch of other ways that you can also prevent overfitting is early stopping. We'll see that. Early stopping is a simple method where what you do is you let the decision tree model be learned and suddenly you just ask you stop it, right? So the algorithm will learn until that point, which is fair, which is good. You can also specify impurity, purity. We'll see all these small tricks. Once the entire tree is formed, you can also remove some of these branches. Very rarely used. I don't use it too much because once the tree is formed, my problem is it's already used all the memory and all that, right? So both approaches reduce depth and improves classification speed happens. You can also use a combination of these. We'll see all of that. So let's look at some of the hyperparameters. Max depth, very simple. We've seen that. The maximum length of a path from root to leaf, right? Minimum sample split, very simple. A limit to stop further splitting of nodes when the number of observations the node is lower than this value. So for instance, in the smoking small example I had given you, it was 6 and 4. I could have given a small condition saying if number of people who are not smoking is less than 3, stop splitting, right? Something like that. Minimum sample leaf is just a corollary from that. Minimum number of samples a leaf must have. So let's say if I keep splitting 10 people, I split, and then after some time, not the last leaf, but one of those nodes has just one element, it's waste, right? Or two elements, I can say no, stop splitting based on that. Don't worry too much about this. You're gonna start seeing a lot more hands-on, and then when you see that, you'll be able to appreciate this. So let's look at this. Minimum weight fraction is also corollary from that. Max leaf nodes also corollary from that. Again, these are all way too many features. Like this is a fully loaded Mercedes-Benz or an Audi. You don't have to work up, figure out all of this. Just 20% of these are enough. Depth and sample split is fairly enough to get great results. Okay. Feature size, maximum number of features that are evaluated for splitting. So we look at one such tree shortly. Okay, what we're going to do is let's look at a small case study. Now, you're not going to be doing hands-on on this. I'm just trying to demonstrate a bunch of small key points, right? So this was a small data set in which 1 in 8 women have, breast cancer. This is really sort of almost real. This is real data. So there's 569 rows and 32 columns. Benign means she's healthy. Malignant means she's cancerous. So diagnosis B is the second column is the one. That's the column of interest to us. Now, and what the, I don't know if I want to use radiologist, the technical word, they actually measure that. So this is not a computer vision problem. This is actually like that cancerous nodule or whatever. They actually measure it, and they actually probably even maybe it's called a lesion also. Sorry, I'm not a radiologist, so I don't know. They actually check the radius mean, texture, perimeter, all that. Based on this, right? If a sample comes in, you want to tell if the lady has cancer or not, right? Extremely huge problem right now. Nowadays, mammograms are taken, obviously, for this. Patient ID is masked. So patient ID is present, the names are masked, obviously, PII, patient identifiable information. Now, I've just, the idea for what I want to tell you is I built a decision tree on this. And when I just kept the max depth as 1, I still get very good results. This is training accuracy, okay? Because the test samples are very less. I get 87.5. And you'll have to take my word for it. However, when I change my max step to 3, obviously my training accuracy increases, right? So it's able to predict it much better. Why? Because when depth was 3, it obviously remembered a lot more of the samples, and samples meaning these n-dimensional points. Okay, so we will so increasing depth is much better, but you also have to have a trade-off because perhaps it didn't do well on the test. Now we didn't look at that. Okay, coming to this. Let's also come across a few more concepts related to how do we go about figuring out the error metrics. Like, how do I understand the error metrics? Now, this is not just a decision tree concept, but in terms of classification, right? So let's look at this case study. Here you have a credit card fraud detection, right? An e-commerce site has been offered a fraud detection system promising a high accuracy. It correctly catches 99% of the fraudulent transactions and incorrectly flags 1% of the honest transactions, right? So just remember this. I want all of you to take a snapshot of this, guys. Can you please take a snapshot? If you have finished the snapshot, type CC in credit card. Good. Okay, remember this because you're going to have a small in-class 2-3 minute exercise, right? Okay, so 3 key questions, right? What are the implications of the retailer mistaking honest transactions as fraudulent? And what will be the implication of the retailer of mistaking fraudulent transactions as honest? And what types of errors are these? Which one is more critical to the business? So we're now slowly beginning to understand how do we deal with classification error metrics. We've looked at a few of the forecasting or the vanilla regression error metrics, which is just mean absolute error. You might even call root mean square error. You could call it mean square error. There are a bunch of different error metrics there. Some sciences give you their own custom regression errors, like I think there's a logarithmic error, etc. But you get the point, right? There you're comparing only the runs or the scores and all that. Here you're checking yes, no's. Okay. So coming back to this. So remember our Bayes theorem and all that, right? So I'm not going to get you to do this right now because I think you've done enough Bayes. For those of you who have not, please go back to those lectures, watch it, double watch it, triple watch it, quadruple watch it, become really thorough, right? So let's look at the condition probabilities. P of flagged fraud, given fraud, is 0.99, right? And P of flagged fraud, given honest, is 0.01. This is what's given, right? Now, other important condition probabilities are P of fraud given flag fraud, P of honest given not flag fraud. So this is where ideally I would want you guys to do this on your own. Spend some 5-6 minutes and do it on your own. If you feel you're not thorough with the Bayes, please, etc., go back, check, and come back. But now I'm going to go ahead and sort of reveal the answer to you, etc., so that you are familiar with at least the previous concepts, right? So if I were to calculate, suppose 1% of the transactions at the e-commerce site are fraudulent, what are the chances the transaction is honest given the system is incorrectly flagged? So you remember the Bayes theorem, and I'm going to just substitute the Bayes theorem. P of honest given flag fraud is equal to P of honest into P of flag fraud given honest and the denominator. So when I do this calculation, when I perform this, I get 0.5. That's actually fairly a high chance, right? 0.5. Now, same example, if 5% of the transactions of the e-commerce site are fraudulent, what are the chances the transaction is honest given the system has incorrectly flagged? It changes to 0.16. Now, what does that mean? By increasing fivefold the chances of fraudulent transaction, my honest given flag fraud changed drastically by more than 34%, right? So just pay attention to this, right? The conclusion here, that the takeaway that you need to have is it which of these numbers is important? So if fraud is rare, too many honest transactions are labeled as fraud. This will be disastrous for the company. At higher fraud rates, the system's performance may be acceptable depending on the size of the transaction and cost, involving contacting annoyed customers and taking the measures. So which of these metrics is actually useful, right? Turns out, so any guesses, guys, before we just move on to the next slide? No guesses? So turns out having one metric, and I think I've alluded to this in some of the previous sessions. Having one metric for a classification is not adequate. It's incomplete. For regression problems, one metric was fine, like root mean square error or may was fairly decent, and I'm happy, right? That's like one meal and I'm happy. But for classification problems, turns out my one dish is not enough. I need to have at least 2 or 3 more, at least one more. So let's look at that one other metric that might be useful. Okay, so the idea is I'm not able to really make very useful conclusions with just one metric, accuracy, or anyone will now enter a couple of more metrics. So let's look at all the metrics possible, and towards the end, what you should have an understanding is we need at least 2 metrics. So in any classification problem, we need at least 2 metrics to uniquely determine how good that classification algorithm is or how good that model is. Okay, let's look at that. So that's the question we're trying to answer now. So for instance, let's look at another example, right? Similar, but this is similar to that e-commerce, but going a little deeper. So now I'm trying to predict if that person is going to purchase my product or not, right? So I have my buyer, predicted negative, and actual negative means 725 folks never purchased my product. So what happened here? 725 folks never purchased my product. Positive. 302, I predicted that they would purchase, and they actually indeed purchased of the total 1260. And you also know how to do this using the cross tab method. Positive, negative. So let's look at this guy. So can anybody tell me what 158 is? 158 was the people I thought would never purchase, but they actually went ahead and purchased. And 75, I definitely thought these guys would never purchase, but they went ahead and purchased. Sorry. I predicted them as they would purchase and they never purchased, right? And this guy here, this 158 is, I predicted they would not purchase and they went ahead and purchased. Are you guys clear about the intuition for this table? If you're clear about this, type B. B means buyer. Just a table. Okay, fair enough. Now let's look at a couple of, let's introduce a few more definitions, right? So true positive means in this matrix, I predicted that guy is going to buy and he went and bought. So that's 302, right? Now, true negative, I predicted that guy would never buy and he never bought. That's 725. So 2 metrics are done. Sorry, 2 of the 2 by 2 is done. False positive again, 75, and false negative 158. So now, should the business be more worried about FP or FN or equally worried about both? Any idea about that? So for the marketing department, FN is problem is the most important, right? Because if a model predicts that the person will not buy, the product will not be marketed, and the business will lose more business, more customers, right? Did you understand this marketing department? Why FN is most important for the marketing department? Guys, did you understand why FN is important for the marketing department? Okay, see. Now, what happened? The marketing department or the sales department is trying to maximize sales, right? Let's say the algorithm was supposed to display an ad, and by whatever the algorithm said, no, this guy is not likely to purchase, so they'll never show the ad, right? But however, reality is or was that that guy would have purchased it, right? So he lost that business, no? Got it. So FN is very important in this case for the marketing department. Clear about that? Everybody understood that? Type FN. If you understood that logic, I need at least 2 FNs. Okay, good. Now, let me spin the question slightly. The courier department of that same business should be worried about what? FN or FP? The courier department should be worried about FP or FN? The courier means like delivery department. There are only 2 answers, Shampi. You've given both the answers. No. What is final answer? Tell me only one answer, which should be final. Aditya says FP. Others, Ashok, what do you say? Samiksha FP. Others? Okay. It should be worried about the FP. Ashok is non-committed. C, no answer. The courier or the logistics department is going to be worried about the FP simply because that manager wants to minimize the cost of the courier. Right? What will happen? So they ship the product, and that guy actually says, no, I never wanted it. Why did you even send me that? Right? Maybe it returned. So that's 2 ways of maybe the cost. So cost is gone, right? So within a business, you can have different departments fighting over the same metrics. Are you clear about that? If you're clear, type CLR, clear. Okay, so be very careful which department you represent. Same thing can happen with healthcare also. Okay, so try to understand this example thoroughly, right? Go back, watch it, because it's very, very deep and profound. So it's not enough to be a data scientist. You also have to know what department is your interest. First your department interest, and only then the company interest, right? So let's look at a few more metrics. So seems like you've understood the business concept, you've understood the data science concept. Let's look at some terminology, because different sciences use different terminology. So the first metric you want to know is called the recall. Okay, so there are 4 metrics you're going to be learning, right? 4 to 5 more apart from accuracy. Like I told you, accuracy is not the only metric that's important. There should be more. So the first metric is recall. Take a snapshot of this. Okay, so the recall is defined always as true positives, that's 302, divided by true positive plus false negatives. That's 460 in this case. Okay, so you got 65%, 0.6. Precision is defined as true positive divided by true positive plus false positive. That's 302 divided by 460. Sorry, 302 divided by 377. So that's the definition. Okay, and the accuracy is defined as 302 plus 725 divided by the entire set of students. That's 1260. Okay, and specificity is defined as true negative divided by true negative plus false positive, right? So these are the four formal definitions that you get. And finally, the F1 score is defined as 2 times precision to recall divided by precision plus recall. Now, why did these names come up? Don't worry about the nomenclature or the etymology, because I told you, different sciences have gotten these. But to holistically, all the error metrics of, or all of the most of the error metrics only fall into these 4-5 different buckets, right? There's one more which we'll see just in a second, right? But like I said, typically you need at least 2 to define your classification metrics, right? So these are formal definitions. Just plug in the values and you start getting the answers. And for us, scikit-learn has a very nice way of sort of displaying these. Okay. Unsurprisingly, it's called classification metrics or confusion metrics. There's nothing confusing about this. Just take this, take the images of this and plug in the formulas, guys. Okay. Now, if you're clear about these formula, type CM, classification metrics. Yeah, you're going to get the PPT. Okay. If you're clear about this, type CM. You're going to be doing, the workings as well. At least the formula. You don't have to by heart it. You don't have to just remember it. And remember one thing, different businesses have different requirements. That's pretty much it. Okay, coming back to this. So for instance, if you look at the blood report, right? If you take a blood test report and all that full body checkup, they actually say sensitivity of the method is 68% and specificity is 92%. So this diagnostic guy is actually correct. He's actually not even, so I don't know about many diagnostic centers, but some of them give these 2 metrics because every instrument is actually doing a classification or a regression or whatever, right? So if they're doing a classification that, you probably are diabetic or not and all that, it has to tell that measure as well, right? So watch out for this. Tomorrow, if somebody is saying, let's say, theoretically, if somebody is saying, you're COVID positive or something, you should also look at the sensitivity and specificity of each. Don't be like some naive page 3 Times of India reader or some blog reader. You have to ask deeper questions. You're a data scientist, so you have to behave like one, right? So there's a few more sort of interesting case studies here. So let's look at that. So there's another data set that I'll let you sort of work on. We're going to run through this, but maybe at home a little later, you can, work this out on your own. So here there's 5,200 men and women, adults, and they had stroke. So again, lots of healthcare examples because I love them. That's very important. And you're supposed to predict stroke, right? So these are CHDs. So you have 15 predictor and 1 target, and you're trying to predict the next 10 years, would you have a heart attack or not, right? So I will give you the data set, on when you ask me. So because this is a really good data set. So let's look at some of the error metrics that come out. Few more error metrics. Like I said, so is there a way we can combine? So I think we understood that we need at least 2 metrics within your confusion matrix to uniquely determine how well your algorithm perform. There's another neat mathematical sort of, I won't say formula, but mathematical definition error metric that's very useful. It's called the receiver operating characteristic or the area under the ROC curve. So we're going to focus on this guy called AUC. Why is it coming? Why do we have this weird name? The etymology is really nice. Feel free to read up upon it. Comes from the radar industry. So let's look at the formula. So the ROC curve is nothing but the one second. Yeah, it's the plot of the true positive rate versus false positive rate, and or sensitivity versus specificity. One more small nomenclature. I forgot to just tell you this. Sensitivity that you look or recall is also called the true positive rate. So here we have that. So there you go. specificity is also called the true negative. Okay, we have looked at accuracy and we have looked at indeed the F1 score. We also have looked at this. So just remember this. Okay, so for the purpose of this ROC curve, we are only focused on true positive rate and true negative rate. So let's go back to this. So when you plot the area, sorry, when you plot this graph and you construct the area, that's when you get the area under the curve. Why is that important? Turns out I've somehow mashed two critical pieces of the confusion matrix into one number, right? So theoretically, I don't need that second. So if I have accuracy, I definitely need maybe one more metric. But if I have the AUC, I pretty much know I can figure out if my model is working well or not, right? So that's a neat slight hack to see how well my algorithms work, right? So again, so let's look at AUC. So measures of discrimination, again, it's like accuracy, but it's also not, because you can see that it's the area under the curve. There's also a percentage on 0 to 100. So AUC is the percentage. One way to also interpret is the percentage of randomly drawn such pairs for which the classification is done correct. Okay. Few more ways of comparing your ROC or AUC curves. Again, this is something that's unique for classification, not applicable for regression problems. If your AUC metric is at 90% and above, it's an excellent classification algorithm. Okay, I repeat. If you're getting AUC numbers above 90%, you can say very well that it's an incredibly good classification algorithm. If it's between 90 and 80, it's good. Less than half is fail, because it's a coin toss. Can you say such a thing? This is very intuitive. Can you say such a thing for regression? Turns out not really, right? So if you get a mean absolute error of, let's say, 498, you really don't know if it's a great number or not. Or if the May is 375, then you know if 375 is better than the 400. Otherwise, you really don't know. So another useful thing, and 90% of the industry problems are classification, right? I've just kept a nice demo. If you have time, feel free to actually look at some more AUC, ROC metrics. Okay, here's one more metric that's beginning to be used. Really, it's taking a lot of prominence, and I felt it's really useful to keep it. Okay, so let's look at this kappa metric. So kappa is defined as total accuracy minus random accuracy divided by 1 minus random accuracy. Okay, so we look at this also a little closer. Just remember this formula. So it's actual false divided by total. We have seen this. So we have seen the true positives, negatives, and all that, right? So if you can just substitute these values, you will get this new metric called kappa. It's beginning to take a lot of shape as well. Again, only formula based, it's theoretical at this time, right? Meaning we'll go back and see these results in our Jupyter notebook. So again, how do we interpret that? So if the kappa metric is above 80%, it's a great model. 60 to 80% is substantial. Less than 0.2 is really not a great kappa metric. So it's actual false divided by total into predicted false divided by total, so on and so forth, right? So that's how we calculate the kappa metrics. I've given you a small hands-on. In the interest of time, I'll let you guys do this on your own. Please do this. Take a pause and calculate the kappa metric here. This is not a great model, but this 10-year hard disk CHD, you can actually find out also what is the true positive rates and all those sensitivity metrics. Okay, cool. One more last case study that I've given you. Again, this is bonus, so you don't have to do too many things. This is a data set that I could probably also as well share on demand. Can you calculate the basic decision tree, and can you calculate the average number of claims? It's a regression problem. Okay, so with that, we will pause the recording for the decision tree piece.